welcome, re-welcome here on this enormous stage. This time, totally different kind of storyline. This is a deep dive, and very intentionally focusing on specific areas of work that are currently reflected in the Spring Framework 6.2 milestones. So this is not a general what's new in 6.2. You've been seeing a few new 6.2 things already here on stage in the keynote, in some other sessions, in some demos. So there's a lot of stuff being refined across the board in Framework 6.2. This particular talk is basically about some of my specific work streams, my personal areas of revisiting parts of the code base in 6.2. That's why it's called Core Container Revisited. We are going to look at basically core application context nuances. It's not totally deep into the details, so I'm trying to explain also the motivation of why we do things at a conceptual level, but we're going to dive just a little bit deeper, and I'm going to show a couple of examples of what kind of effect this is supposed to have. In terms of the topics that we are going to cover, it's basically two categories. We're going to dive a little bit into the autowiring algorithm. This autowiring behavior is more sophisticated, more nuanced than probably you have seen before. In most cases, it's been used for very simple purposes, but it's actually a sophisticated algorithm with several steps. And it's being revisited in 6.2 now in very specific forms. The other area is container initialization, also a bit more of a infrastructural topic, I suppose. And for the first time in quite a number of years, in 6.2 we're trying to revisit some core container behavior, down to the degree of the level of locking that the core container uses for runtime interactions. It's a totally different locking arrangement in 6.2. We're talking about a new feature or a feature area called background initialization, both the state of the art of what you can do right now in existing framework versions and what's new in 6.2 there. And we're also going to revisit the notion of lifecycle management briefly at the very end. Lifecycle as in the Spring Core Container Lifecycle, Smart Lifecycle arrangement, which has been significantly revisited in 6.1 and gets a bit more of an overhaul in 6.2. All right, so much for the sort of agenda. The motivation, the general motivation for all of this is that in 6.2 we're trying to find long-standing issues. We went through the issue tracker. We basically listened to everyone who had an opinion on things that matter for the core container, and we're trying to consolidate all of this feedback and some of these long-standing issues, 10-year-old issues often from the issue tracker. We're trying to consolidate all of this into this revision in Spring Framework 6.2. So this is a bit of a long-planned and pretty broad and deep revision in terms of what we've considered, what we've been considering as input here. Whereas the outcome of what we actually do in the core container, what we do differently in 6.2, is actually quite to the point. And I personally really appreciate that kind of balance. A lot of input, a lot of use cases presented, and pretty straightforward solutions addressing several of those with very specific and reasonably local changes in the core framework code base. All right, so much for that part. Let's dive into it. The autowiring algorithm is obviously a kind of a key piece of the core container, right? A sort of crown jewel, if you will. The autowiring algorithm was initially conceived to be just straightforward bean references. There wasn't basically much of an algorithm. You had, in the XML bean definition days, you basically had just a reference to some other bean by name. But it pretty quickly became a bit of a convention-based arrangement. We had autowiring by type. We had autowiring of constructors, which is also by type, by parameter types. We had field injection, which is also a by type arrangement if you use that autowired. We had then the introduction of GSR 250 at resource, which was once again by name. At resource points to a specific name or uses the local field or parameter name to look for a specific target component by name. So there's been many different variations of this. And some of it remains actually. At resource is still specifically processed. XML bean definitions is specifically processed. What we talk about here today is what most of our applications use today. It's basically what happens when you do add autowired, and it's also what happens when you do constructor-based autowiring. Implicit constructor-based autowiring, where you just have a constructor with several parameters, no specific annotations, but we basically resolve them just like if the constructor was annotated with add autowired. So this particular algorithm, this kind of common algorithm, is type-based, which means as a first step, we're going to find all matching beans by type. We're going to go through everything that's been registered with the core container. We're going to identify the type for each particular bean. And there's something you declared, like your constructor parameter. We're going to look for type matches. We're basically literally going to go through all of the registered bean definitions and going to find all the ones that match by type. In many cases, you will only have one bean that actually matches that type. Right? So the simple case is basically you declare a type and there's exactly one bean that is assignable to the type, and we're basically done, right? Then it's simple. But what happens if there's more than one match for that particular type? Then it gets pretty nuanced. For a start, there is a qualifier model. The qualifier model is also reflected in the GSR 330 at inject arrangement. Qualifiers are used to basically narrow a set of type matches further down to a particular bean that matches that type and a specific qualifier. So a qualifier is local within the set of type matches. It's not a general global qualifier. It's locally applicable within a specific set of matches. So we basically have all the matches by type. Then we filter those, all of those that also match declared qualifiers. We're going to see an example in a moment of what that can look like. But even that might not be sufficient. What if there's more than one bean remaining? So we have like 3 matching beans by type. 2 of them match the qualifier. That's allowed, right? A qualifier does not have to be unique. So if the remaining result still has more than one candidate, we have this notion of a primary candidate. You might know this as at primary, when we're going to get to the revision of this in a moment. At primary happens in this 3rd stage. That's a bit of a simplification of the algorithm actually, but roughly matching what it actually does. So we can also select a primary candidate, which basically says like, dear container, if you find yourself facing more than one matching bean still, use this if you're in doubt. That's the one to use. Right, and there's a less well-known 4th step down below here. Since you don't need to use those things above. You don't need to use qualifiers. You don't need to use the primary flag. So there might still be a scenario where we have a set of matching beans by type, no qualifiers, no primary flag. What do we do? As a last resort, we compare the declared parameter name to the target bean name, and if the parameter name matches a specific candidate by bean name, that's the one we're going to use instead of failing. Right? It's originally has been conceived as a kind of last resort. But it's not just that. So I don't want to downplay it even in its original motivation. It's a simple way to express which of the beans you mean without having to use any of the other mechanisms, without having to reason about qualifiers, without having to be aware of the primary flag. You can basically, within the set of type matches, select a candidate by bean name, effectively, by declaring that bean name locally as a qualified name on your injection point. Whew. So that's kind of, in a nutshell, what the algorithm does. A little more nuance that's not relevant for the course today is being left out. So what does this mean? Just illustrating it a little more. The simplest case is a match by type. If there's only one bean of type data source, you can basically do a reference that's, in this case, not a constructor, but it's constructor-like. It's an add-bean method with an argument, which is treated, a factory method argument is treated just like a constructor argument. So it's basically every time I say constructor, you can think factory method at the same time. So this is matching by type. If there's only one bean of type data source in the context, there's nothing to worry about. We'll find it. It's a unique match. No concerns. If the data source happens not to be unique, this is an arbitrary artificial name here, you can add a qualifier. We actually recommend qualifiers to be more specifically named, so you can use it. You can use like at order module, at order domain, at accounts or whatever. You can use a name that has a meaning, that expresses something in your layout, in your code base, in your architecture. But fundamentally, it's just an annotation that you build yourself, that you can build yourself. You declare it at the target bean and also for what we call the injection point down here. So where it's being injected. It's type plus qualifier. The qualifier only has significance within the set of type matches. So the type match always comes first. It's a my-qualified data source. Right? It's both combined. Now, let's revisit this notion of auto-wiring by bean name. There was this kind of little fallback we had at the very end. If you're not using qualifiers, if you don't build your own qualifier notations, you could just use a parameter name, express a parameter name for your constructor argument, for your factory method argument, and match the target bean that you mean by name. In 6.2, we actually make that first class, or we put it to the forefront for a performance optimization, whatever way you want to see it. There's basically a fast path for bean name matches, because one of the common concerns that we heard for many years is that at resource with a straight name referenced in the annotation basically is a very quick lookup. We go straight into a concurrent hash map and look up a pre-registered singleton instance by name. It doesn't get faster than that. Whereas the auto-wiring algorithm, I mean, even if you just read or remember the 4 steps before, it's obviously more expensive. We do type matches, we cache those type matches, but they are expensive to come up with initially. Qualifier matches are also somewhat expensive, or at least more expensive than a hash map lookup. So in 6.2, we basically have the same algorithm in place, only revisited in very specific nuances internally, but it's basically the same algorithm, the same 4 steps. But there's a fast path now. We basically say, if you have a constructor parameter, a factory method parameter, and it happens to have a well-defined name, so please compile your code with dash parameters. You basically know that story in Spring already, that we rely on parameter names in quite a few places. So if we have that well-defined parameter name, there's a fast path where we basically say, like, optimistic assumption, is there a pre-registered singleton instance of that name? If we find an existing potential match of that name that's pre-registered, then we kind of work our way back through the algorithm. We use the other steps as basically conditions that we need to meet. So we basically say, like, oh, there is a bean that basically matches this injection point by name. Does it match the declared type? Does it match any qualifiers, if there are any? Do we have primary candidates for these types? If none of those things kick in, we basically are left with a fast path where we can say, like, okay, then we actually mean this bean by name. So we kind of have an optimistic assumption. This could be the candidate that we're looking for. Then we just assert that it meets the type, the qualifiers, and is not being overridden by some other primary bean. and then we look it up straight away. So what does this look like? It's actually, the explanation probably sounds way more complicated than it actually is in practice. Just declare your parameter name, like down here, with the very same name that you use for the bean name. That's for add-bean methods, that means the add-bean method name needs to match the parameter name of where you're actually using that thing. Those pieces will typically live in distinct classes, right? So it's just for the purposes of the code fitting on a slide, but those points can be in totally different configuration classes, obviously, for everything I'm showing here. But so wherever they are, try to meet the parameter name, try to match it by name with the target definition. That alone is sufficient as a performance optimization for making this lookup as fast as possible. A variation of this, it's actually not new, so this worked before. You can, instead of meeting the parameter name, of relying on the parameter name, you can add an explicit qualifier. Add qualifier target bean name. That worked before, but in the old version of the algorithm, it was the last step. It was this last resort, right? We could express this with a qualifier with a string attached to the injection point. If there's no such qualifier on the target bean definition, as a last resort, we match it against bean names there. So previously, this wouldn't improve the lookup performance. But now, this exact same arrangement, so either of the two, right? Which is totally compatible with Spring versions back to 3.0. But as of 6.2, it operates with significantly better lookup performance at runtime. For a small application, say for a small application context with just a couple of beans, right? It won't make much of a difference. How could it? But the larger an application is, the more bean definitions you have registered with your core container, the more difference it makes. And we have seen applications with not hundreds, but thousands of beans, 10,000s of beans in some cases, living in a single application context. It makes a huge difference in those kinds of setups. And it's an easy convention to meet. You might even accidentally meet that convention already. Right, so that's one of the things we kind of came up with as a solution to a common set of problems that we were facing. Revisiting this notion of primary beans, remember? There's also you can also flag a bean as primary. If there's a set of type matches, we are going to use, within that set of type matches, we're going to use the primary candidate if there is one. This notion of primary is also being revisited in 6.2 here. We now have primary beans, we have the regular beans without any flagging, and we now have a new notion of fallback beans. So it's now 3 categories of flagging instead of 2. So previously you could have just a regular bean. We would always use that if it's unique, but if it's not unique, it could be overridden by a primary bean. If we find 2 matches by type, one is primary, one is not, we use the primary one. Fallback beans operate the other way around. If a set of type matches has like 2 beans left, one of them is regular, no flagging, the other is a fallback bean. We're always going to use the regular one. Or more specifically speaking, within a set of type matches, if there's only one non-fallback bean in it, that's the one we're going to use. So if there is more than one data source, in a nutshell, that's what you can do right now, already available for many years. You can flag one of the beans as primary. That's the one we're going to use if not specifically qualified otherwise. Right? So the other one we're always going to ignore unless it's specifically requested through a qualifier or other kind of indication. So primary as a simple marker for use that one if in doubt. Fallback beans simply operate the other way around. You leave the original definition as is, you add fallback to the other. And even if there's more such fallbacks, that's no problem as long as one non-fallback bean is left within the set of type matches. That's the one that's commonly going to be used. The others are injectable, but you need to specifically request them by a subtype or by name. Otherwise, they serve as a fallback only. The point here is, another common request that we got on the issue tracker, you might define those in very distinct places, maybe in different modules of your system, maybe in different library jars. So you might not be able to add a primary flag to the original definition. You have to keep it as it originally is. It's not in your hands. But you control the new ones that you're adding, that you don't want to be injected regularly. So you are in control of the other data source definition down here. You can add a fallback annotation there, whereas you are not able to touch the one above. So it's a very simple kind of inversion of the flagging. There's quite a few issues on the issue tracker, so there has been a lot of discussion around this. In order to arrive at this, it took a number of years to arrive at this. All right, so much for the autowiring algorithm. There's a bit more nuance to this. I'm going to summarize it at the very end. Just in a nutshell, in 6.2, we have very specific new mechanisms, variations of the mechanism in place for performance optimizations and also for more flexibility in combining artifacts from different sources, from different teams into the same application context. All right, let's move on to container initialization. You might not typically be exposed to this, but on startup, there's very specific steps being taken by the core container to initialize itself. An application context has it's about 15 steps that it goes through to initialize itself in a certain order of events. Part of this is initializing all the non-lazy singletons in the application context. So the core container will go through the register bean definitions. It will identify the singleton bean definitions among those. And unless they have a lazy flag attached to them, we consider them eager initialized to be initialized eagerly. So the core container basically takes those and requests them on startup. It builds the instances as it bootstraps. Then and only then, the application is willing to accept requests from the outside. So as part of the bootstrap sequence of a Spring application, a Spring Boot application in particular, all of those non-lazy singletons are going to be initialized. In an ideal world, you would never have to worry about this. We initialize those singleton beans in the order of registration. So if you tightly control the order in which they are defined, that's exactly the order in which they are going to be initialized. But it's not the only thing taken into account. We need to take the dependency graph into account. If we are starting to initialize a repository bean, and it has a reference to a data source, a non-lazy reference to a data source, then we need to initialize that data source first. Semantically, an injection point, a non-lazy injection point where something is being injected into another bean, semantically comes with an assumption that that other bean that you get there, the data source, when you receive it, is already fully initialized. So in a regular scenario, there are conditions attached, expectations attached, that you get a fully initialized component that fundamentally you could start using it when you receive it. You have a repository factory method that takes a data source. You could start using that data source right there in the factory method, semantically. It's not necessarily what typically happens in practice. But that's why we have to initialize according to the dependency structure. So if a repository bean takes a data source, we're going to initialize that data source first, then the repository bean. If you want to influence this order of registration, we have a depends on annotation where you can say like, it depends on that other bean. That's the one way to override this in addition to the dependency structure itself. You can basically force the initialization of some specific other bean before this bean that you're currently declaring is being created. So there are ways to override it. But as I said, in an ideal world, you wouldn't have to worry. It just magically resolves all the singleton instances and the graph that results from it. It just magically resolves on startup. But sometimes you have to debug your way into it in what actually happens there, and that's when these rules start to be, start showing, right? On shutdown, for completeness, that's not actually our primary topic, but on shutdown, we also destroy bin instances, singleton instances, in the inverse order. So the last one created is the first one that we are going to destroy, which also means that, say, the data source and the repository bin, we're going to destroy the repository bin first. It could still use the data source on destruction, and only then, when all of the dependent bins have been destroyed, then we're going to close the data source. Right? So this idea of the right order of initialization also translates to the right order of destruction on shutdown. Basically in the inverse order of what we did on startup. All right, why is this relevant? It's actually this little note here. All of this, all of these singleton creation steps for every particular singleton bin, they all happen within what we call a singleton initialization lock. The reason for this is that a bin and its dependency structure really needs to be seen as sort of one step. If you have more than one thread potentially trying to obtain a singleton that hasn't been created yet, you get into trouble pretty quickly if this is not an atomic step that is being taken there. So there is a serious degree of locking in the traditional Spring Core container for creating a singleton and its dependencies. As part of this assumption, we rely on a bootstrap thread, right? There's basically one thread that goes into your application when it starts. That's a single bootstrap thread, the one basically that runs your main method. That thread is being used for initializing the entire application. So all of this locking happens within a single thread, which basically usually means that the locking doesn't have too much effect to begin with, at least for eager singletons. For lazy singletons, they could be initialized whenever they are first used, right? So sometime at runtime, when someone sends a request that touches a particular singleton, if it hasn't been initialized, and since it was marked as lazy, we might actually initialize it late. So then actually that locking also kicks in. So what are we doing differently in 6.2? Previously, we used synchronization. There was traditional synchronization for creating each singleton. As of 6.2, the locking is entirely reentrant lock based, which gives us some extra flexibility. With a reentrant lock, you can basically check whether the lock is already being held by some other thread. So if our main bootstrap thread goes through the list of singletons, creates them one by one, then it runs into a particular singleton, and say that singleton has some kind of initialization method where it starts an asynchronous thread that potentially touches other bins, and that bin, that's a custom bin that you implemented maybe, and that custom bin then blocks waiting for the result of that asynchronous thread. Previously, we had no chance other than basically deadlocking, right? The arrangement could easily run into a situation where that other thread was waiting for the singleton lock, the original thread held onto the singleton lock and was waiting for the result from that other thread. That's not going to resolve itself. So typically you wouldn't run into this because we recommend a single bootstrap thread, but it was easy enough in certain scenarios to happen. You can't prevent other threads from executing if they're being used in some custom bean classes, maybe in some library code that you're integrating, or even if you kill the JVM, if you send a shutdown signal during the bootstrap phase, then there's an asynchronous JVM shutdown thread kind of kicking into the core container and saying you need to shut down now. Even then, there's another thread that potentially triggers destroy methods, which can trigger other beans, and you can easily get into the same kind of trouble. There are scenarios that where we had to accept that deadlocks were possible. So as of 6.2, we use reentrant lock, and there's a new notion of a main bootstrap thread. That's the one that consistently holds the singleton lock in a regular startup. Other threads that, for any reason, execute at the same time have lenient locking. They try to obtain the lock, so if they are in the position to do so, but generally speaking, they are going to realize that the lock is already held by the main bootstrap thread. They can go into the singleton map. They can not only look up beans that worked before without locking, they can also try to create a specific bean that's not created yet outside of the general singleton lock, under the optimistic assumption that it's an independent bean that doesn't really touch other beans that could get in conflict with the main bootstrap thread. So there's always a bit of an extra assumption, a bit of an optimistic assumption baked into these. The good thing here is, in all of the scenarios that we're aware of, so asynchronous threads started in some init methods, the JVM shutdown thread, as mentioned, in all of the scenarios that we are aware of, this is sufficient to resolve the problem. The other thread can lazily create an independent singleton bean instance without waiting on the general singleton lock. And we still have consistent singleton locking in the main bootstrap thread. So it's kind of the best of both worlds. Right, so much for a bit of a deeper discussion of the locking arrangement. If we go a level higher again, the already mentioned main bootstrap thread is basically well known. Every Spring application in history used basically a single startup thread by default, leading to this consistent initialization of beans and their dependencies. Now, as of 6.2, we have this lenient locking arrangement where we don't need to be afraid of other threads touching the core singleton registry. Or at least we don't need to be as afraid of as before, because there's no immediate risk for deadlocks anymore. This opens up a bit more room for using multiple threads to initialize an application. That's a very common feature request, highly voted, long-standing, parallel bean initialization. I think it's the name of the GitHub issue. It's been out there for a long, long time. Even at this point, we are not actively recommending a multi-threaded bootstrap arrangement. It usually does not help as much as you would expect in terms of the bootstrap time. And it leads to less predictable startup behavior because you're not in full control over the order of creation. In particular, also in terms of reproducibility. Sometimes the order might not matter, but what might matter to you is that if you bootstrap your application once and again, you want the exact same order, whatever order it was, when you rebootstrap, right? And that cannot be guaranteed with multiple threads. So in that sense, it's less predictable. But that might still be something you're willing to accept. We already have background initialization options, so that's not a totally new topic. Maybe you've seen, or maybe you've run into this, the JPA setup, Entity Manager Factory bootstrapping, for quite a number of years already. We have this notion of a bootstrap executor there, where we use a different thread, essentially, from that executor for bootstrapping the persistence provider. So we're basically doing the Hibernate bootstrap in a separate thread. And only at the very end, when it's finished in terms of that asynchronous bootstrap, only then the Entity Manager Factory handle is going to be usable. The twist here is, and that's an important twist, we can expose and inject the Entity Manager Factory handle as a proxy before. It's not actually usable yet, but we can pass it into other beans. So some repository could accept an Entity Manager Factory reference and only start using it later on, when the requests come in some specific service methods, some specific operations. And in the meantime, in the background, basically Hibernate keeps bootstrapping. Only when the entity manager factory proxy is being called, then we're going to block waiting for that bootstrap to complete. That's a very specific background initialization option that we've been having for a number of years. This used to be, and to some degree still is, the recommendation for doing asynchronous bootstrapping. In any custom bean of yours, you could basically mimic what our entity manager factory bean arrangement does. You could internally create some resource on a background thread, expose a proxy in the meantime, and only when that proxy receives an actual operational call, only then it's going to wait blocking for that asynchronous thread to complete. So that's kind of a safe option. This did not require any specific support in the core container. So if you think about it from a framework perspective, the core container itself just has its main bootstrap thread and does whatever it does on startup, right? What it always did. It's an internal decision within a particular bean implementation that you choose to use a background initialization thread for a particular type that you expose, and you can benefit from the characteristics of that particular type. So if you know, like for an entity manager factory, if it's very likely that in your setup, it's only going to be used very late, then that's a characteristic you can benefit from. You can make assumptions, derive assumptions from the particular type that you're exposing. So that used to be the state of the art. It still is the state of the art for certain purposes. What's new in 6.2 is a background initialization option for individual beans. You're basically using the bean definition level at bean factory methods, and you express that you want that particular bean to be bootstrapped on a background thread. That's a core container feature. The core container has support for background initialization at that level, and it has a configurable bootstrap executor, basically the thread pool you want to use for background threads, in order to use that whenever it encounters an @bean bootstrap background declaration. None of the standard beans are marked for background bootstrapping. We don't expect any of them to be marked for background bootstrapping. That's a choice that you make for particular beans in your system, in your setup. So it's very much an opt-in mechanism. This has quite a lot of consequences. We're going to see some variation of this in a moment. If you want to bootstrap a particular bean in the background, and some other bean requests that bean right afterwards, right? We're basically going to block waiting for that bean to be fully initialized, and only then we are going to inject it. That won't buy you anything if the main bootstrap thread insists on that bean being available right afterwards. So this is meant to be used in combination with lazy injection points, where you basically inject proxies for the target bean type. And you typically do this, just like for JPA entity manager factories, you typically do this if you know that that particular reference is only going to be used later on. You accept it in the constructor or in the factory method, you store it in a field, and you know you're only going to use it later on. Then and only then, background bootstrapping for that target bean might make sense. The other thing is a reproducible dependency order, or a well-defined dependency order to begin with. We do not let background marked threads forcing the initialization of beans in their background thread. It's basically independent steps for that particular bean. That bean and only that bean individually is being bootstrapped on a background thread. If it refers to dependencies, if it insists, if it needs to have those initialized first, then make sure that it actually happens first. Declare it first, or use @depends-on to force the initialization of those other beans first. That's part of the preparation that you need to do, the setup that you need to apply to make that mechanism work in your application. If that's not a problem, if you can set up your beans to meet those requirements, then it's actually pretty straightforward. You could declare, for example, your data source bean to be bootstrapped in the background, and your repository bean accepts a lazy data source. So it actually receives a data source proxy. So this definition here does not insist on the data source to be fully initialized. It's a lazy reference. @lazy basically says, I'm happy for this reference that I'm being given to not be completely initialized yet. I'm going to use it later on. Obviously, I will have to need it initialized whenever I start using it, but that's not right now. That's what @lazy says. So this makes a huge difference. If that lazy marker is not here, it's going to insist on a fully initialized data source. It's going to basically block until the background thread returns, right away, right? So these two things go together. @lazy is a mechanism we've been having for many purposes over many years, right? @lazy is a well-established part of the Spring bean definition model. Bootstrap background, that's new, right? But it works nicely in combination. All right, so I'm going to summarize the parts that are new in 6.2 at the very end in just a few minutes. One quick additional note to complete this kind of tour through core container concerns. What we mean by lifecycle management is a very particular arrangement. I've already been hinting at the application context bootstrap to be more sophisticated than it usually sounds. So yes, we initialize all the regular singletons. We create them, we call their post-construct methods, we expose them in the singleton registry. Yes, we do this. But at the very end, there's another step. We look for lifecycle beans that request to be auto-started. After all the regular singleton beans have been created, there's this one more step where we basically do start callbacks on components that want it. So we mean lifecycle in that context. It's a start-stop arrangement. This is typically used for asynchronous workers. So some of the components that you might be using, the JMS message listener containers, or if you're using, say, the WebSocket support or Spring integration, many of those components use this lifecycle arrangement. They rely on an auto-start signal at the very end of the startup process. And there's also the inverse arrangement for graceful parallel stopping on shutdown. So an arrangement where before we start destroying singleton instances, we actually send stop signals to the lifecycle beans in parallel in certain phases, so they have a chance of asking their asynchronous workers, their asynchronous tasks to complete before the actual destruction step comes in. So this is kind of an additional mechanism on top of the standard creation and destruction arrangement. We have a start-stop arrangement in addition to this. This mechanism has been significantly revised in 6.1, in particular for a specific capability of that arrangement. It's not just start on startup and stop before destruction. It can also be used during the runtime, during the lifetime of the application. Basically, you do a stop call and you do a start call a little later. It's a pause restart arrangement with the same callbacks. So that's an additional capability of a lifecycle component. It can be temporarily stopped and subsequently restarted. That's a mechanism we've been using for our crack support for snapshot arrangements, where we basically need to bring the application to a halt so that there's no activity anymore. Then we take this like process snapshot that crack requires. And after the snapshot has been taken, after it has also been taken out of hibernation, if you bootstrap from that, your JVM from that snapshot, right afterwards we're going to restart all the components that need restarting. It's the very same mechanism that's also built into the core container at a slightly higher level, in addition to the core construction and destruction arrangement. Right, so in 6.1, there's actually more components participating in this lifecycle management, even the thread pools. So if you happen to have thread pool task schedulers, task executors, managed thread pools, even those are going to participate in a pause restart arrangement, trying to stop all the asynchronous workers, all the asynchronous runnables that they manage. It's usually recommendable for those workers to be aware of the stop signal themselves, but if they are not, then the thread pool basically waits until those tasks complete and only then considers itself fully paused. So we're actually taking this pretty far, and it's an enabler for quite a few recent arrangements that we had, like the crack snapshotting support. I've already been hinting at the phases arrangements. Lifecycle components can group themselves into phases, so that we start a certain group of components first and another group later on. They are using phase declarations. Those are basically just integer values. These integer values can make a lot of difference. Like, say, if you have a message listener container and a general thread pool, are you going to stop the message listener container first or the thread pool first? So which one comes first, right? That's implicitly determined by the phase value that's attached to those. We have default phase values, so usually you don't need to worry because the default phase values just work it out for you. Unfortunately, there's conflicting requirements, right? Sometimes you need to customize those in order to meet your particular requirements. So a reminder, those phase values are actually configurable. Every smart lifecycle bean usually has a set phase method where it can be configured. The opportunity in 6.2 is that we are revisiting the default values. There has been some common suggestions, in particular for the default phase that we use for our schedulers and for our executors. We've been revisiting that in 6.2 to meet an existing convention that Spring Integration introduced. So if you want, in particular, if you are integrating with Spring's lifecycle management, in 6.2, hopefully the default phase arrangement that you're integrating with leads to a better experience where you don't need to customize your values, where your standard lifecycle components have a chance of being stopped at the time that you expect them to. The default phase arrangement is hopefully more intuitive now. But yeah, if it's not for your purposes, keep in mind that phases are configurable. Make use of this if you need to. So if you are defining your own, if you go to the extent of defining your own thread pools, your own task executors, your own task schedulers, there can be several of those. Maybe one of them needs to be stopped earlier, the other at the very end, depending on what it's used for. You can have distinct executors and schedulers, more than one of each, with distinct phases attached. Keep in mind that that is a configurable arrangement. You don't need to take it as it is. In standard Spring, you can influence what actually happens, in particular for highly concurrent messaging applications. That's often a way out for graceful shutdown arrangements that you need to provide. All right. So much for everything I meant to cover today. In summary, I've been showing quite a few things that have been out there in the Spring Component model, the configuration model, for many years. Some of it may be introduced in recent years. A few things that are new in 6.2, and then let me take the opportunity to summarize those quickly. The part for matching with parameter names matching the target bean names, that the part where this actually leads to faster autowiring, to faster resolution, at runtime, that's new in 6.2. With the primary fallback arrangement, primary beans have been out for many years, have been available for many years. The part that is new in 6.2 is the equivalent counterpart at fallback, marking specific beans to usually be ignored and the regular bean to be taken instead. That part is new in 6.2. For background initialization, built-in custom initialization within specific bean classes has been out there for quite a while. Quite a few components do this. We do it ourselves for our JPA bootstrapping if requested to do so. The part that is new in 6.2 is the declarative at bean bootstrap equals background arrangement. That part is new in 6.2. Background bootstrapping at the bean definition level for particular individual beans. We typically combined with at lazy injection in wherever they are used. And for the lifecycle management arrangement, a lot of the revision actually happened in 6.1, so last year, or in basically the current generation of Spring. What's new in 6.2 is revisiting the default lifecycle phase values in order to be more intuitive in a typical modern-day messaging or asynchronous processing setup. So think Spring integration, Spring batch arrangements, a scheduler, executor, maybe several executors. That arrangement should just work without you having to customize the lifecycle values. So the revised default values for lifecycle phases is also new in 6.2. A reminder, 6.2 is currently in pre-release stages. So we have milestone 3 out, and whatever you've been seeing in the demos at this conference is usually using 6.2 M3 with current boot, so the framework version manually upgraded. 6.2 GA is planned for the November release train, along with Spring Boot 3.4. So it's an opportunity to give the new core framework generation a try. We'll have Spring Boot 3.4 milestone soon, but you could even use it with Spring Boot 3.3 and just manually upgrading the core framework version. Right, so that's what's coming up. Half a year to go. If you have any feedback on this, if you want to give this a try, and let us know that there are regressions in for you in your scenario, or also to let us know that there is actual significant benefit in your scenario, so that our assumptions actually work out, we'd be happy to hear from you. So give it a try if you have the chance, and it's going to become generally available in about half a year. So, thanks for your attention.